What happens when you take the difference of lambda? Okay, first of all, lambda 2 and lambda 1 are distinct, right? Fine. What's their difference, though? What's lambda 1 minus lambda 2? 4, 6, right? Down here, what's lambda 3 minus lambda 4? Minus 4, yeah, minus 4 minus 6. My point to you is that those are both units in the direct product algebra. What happens when we take, for example, lambda 1 minus lambda 3? What do we get? What's lambda 1 minus lambda 4? What's lambda 2 minus lambda, 3? What's lambda 2 minus lambda 4? What are these? 1 minus 3. 4, 0. 1 minus 4. 0, 6. 2 minus 3. Thanks. I was talking myself out of that. Signs are not going well for me. 2 minus 4. So get minus 4, 0, right? My point to you is that these pairs, if we think about pairing lambda 1 with lambda 3, lambda 1 with lambda 4, lambda 2 with lambda 3, lambda 2 with lambda 4, these pairings are not allowed in my way of thinking because the difference between these eigenvalues, while non-zero, we don't care. The fact that the difference of the eigenvalues are zero divisors in the algebra is damning. That's the trouble. This is what I learned studying the nth order problem, is that to get a fundamental solution set from exponentials, it wasn't enough anymore. Like in the ordinary over a field, it suffices to assume that the arguments of the exponentials, the multipliers, e to the lambda t, if you have like e to lambda 1 t, e to lambda 2 t, over a field, if lambda 1 is not equal to lambda 2, you have linear independence. But over an algebra, if the difference of lambda 1 and lambda 2 is a zero divisor, e to the lambda 1t and e to the lambda 2t can be linearly dependent. So it's not enough to look for distinct eigenvalues. We need to look for the difference between the pairs being a unit if we're going to put them together to form a basis. That's the structure here that we should be able to prove general theorems about. If I could state the theorem cleanly, this is the thing I think that I'm conjecturing. Because to me that's the pattern that we're seeing here. That's why 1 and 2 work together. That's why 3 and 4 work together, but not the other combinations. So I don't know, like this book that we were looking at, of course, right? Matrices over commutative rings. I mean, this is a great book, right? It's nice. I mean, his goal is not solving differential equations. His goal is saying when is the matrix diagonalizable over a ring, and that's what his theorem told us last time. If you can pick a free module basis from your set of eigenvectors of the roots, then it's diagonalizable. So we're interested in something that's a little bit more nuanced than that. We're interested in describing, what does a solution set look like to one of these systems of differential equations over an algebra? And how can we sort of cull a solution set from a given set of eigenvectors? And if you have an embarrassment of riches, if you have too many eigenvalues, how can you be careful to select the right subset of those eigenvalues to find the right kind of eigenvectors from which you can actually build what you need? So I should try to write down theorems that we could prove to be more systematic here. I'm not sure. Do you guys have any ideas about what we should do next year? I mean, I'm happy. We found the example, right? This is the example we've been. There's other things we could try to pick at, like What about the example of a 2 by 2? Well, first of all, one thing we could look at, what is this in hyperbolic notation? What does this example look like if we change over to like 1s and j's instead of 1s and 1 minus 1s?
That book shows like all these like relations that we have between like the eigenvalues of it.
No, it does not show these.
So that these patterns apply in all situations at all. Like,
We do not know that. We do not know that. I speculate that because I've seen these patterns before in my paper that I wrote with Nathan Bedell.
why don't we try and like generalize it to all matrices and see how far we can go with power?
I'd like to do that. That's one thing I'd like to do. Try to actually be a little bit more systematic about the basic linear algebra over a ring here. The other direction would be to try to study the question of complexification in the sense that suppose you can't solve your characteristic equation over the algebra. Suppose we're in the opposite kind of herding. Instead of having too many, we have none. Then what do you do past there? Like, is there some kind of extension of the hyperbolic numbers or the direct product of R with R such that in that extension we can find some kind of vector in the extension algebra such that from that vector we can construct solutions to the given system? How does that go? We know that goes because we have the general construction of the matrix exponential. I can prove without exception, you take the matrix, you stick it in the matrix exponential, you multiply it by the algebra variable, e to the algebra variable times matrix is a fundamental solution matrix to the system. So I already know that we can, I already know how to construct the solution in some sense, but that's kind of like, okay, well, I know how to construct it as an infinite series of powers of the matrix in the algebra. And that's a thing, right? But I'm looking for more than that. I want to understand how the eigensolution story plays out. And in this case that we're in the sort of the no roots case, then what can we do? What are strategies we can exploit to try to unravel the matrix exponential solution? In the ordinary case, we use chains of generalized eigenvectors with great success, or generalized complex eigenvectors. So this is what Kang was trying to work on, was trying to find the analog of the Jordan form for the matrix, because if you could find that, then you could put that together with the matrix exponential. You could do the similarity transformation of the matrix exponential. You weren't thinking this, I was thinking this. You could do the similarity transformation with the matrix exponential to rip apart the solution into its nice pieces. Like that's the extra thing that comes if you could find that way to take the matrix over the algebra and like put it to something nice. Then we could use that something nice in the similarity transformation with the matrix exponential solution to rip back a nice solution over the algebra, basically. I mean, that's something like that. Ah. Yes. Hmm.
But that's just a calculation. I don't really find anything.
It's not. You don't think it's nice. It's not nice in the way we're talking about. I mean, it's more like, I think if I understand your result correctly, King, it's something along the lines of this. In linear algebra, I can say the following: I have T from vector space V to vector space W, linear transformation, right? From dimension n to dimension m. Well, I can tell you, without any further data, other than that T is linear, that there exists a basis beta for V and a basis gamma for W, such that the matrix of T with respect to beta gamma has the form identity matrix, P by P, zeros. Right? There exists a change of basis which makes the matrix look like that, because all I do is I take the basis for the range, put the kernel basis at the end, and extend to the things that map non-trivially to the range. And by so constructing such a thing, and then similarly arranging the codomain basis to match up with it, I get the identity padded with zeros. If I have the freedom to change the basis in the domain and the codomain separately, I can always do this. What makes Jordan form so much more special is that we force ourselves to change the basis in the domain and the codomain simultaneously. We're really looking at an endomorphism from V to V where we're changing the coordinate system on both at the same time in such a way that it kind of reveals some special structure to linear transformation. That's the ultimate goal of linear. So you found, I think you...
I didn't find anything.
Not yet. Some kind of decomposition. I need to look at what you did again, because I think we're about where I should look at it now. Getting pretty close anyway. But I agree with Jess. We should try to think about, if you can think of a theorem that you'd like to state for us to prove at start of next class, just do it. We'll try to prove it. We can go that direction. I don't know, like we have a lot of creative directions to go from here. So you guys be ready for the final.
So I think that you said it's in lemma 17.
So it is in the book. I just haven't read the book. That seems entirely possible. Lemma, which was?
17.9 on the first.
Lemma 17.9, let A be an n by n matrix over R. Delta a subset of the roots. Suppose delta has the following property. If D and D prime are in delta, and D is not equal to D prime, then D minus D prime is not an element of the zero divisors of R. Then the sum of the eigenspaces over D is the direct sum of the direct sum. Yeah, so he's saying that it's similar.
Yes, sir.
Maybe the same. Maybe it's already what are...
Well, this one we have respect.
It basically, this theorem says, this lemma 17.9 on page 220 of this wonderful book, essentially says that if the difference of your roots, is not a zero divisor and not equal and not zero, because his z of r doesn't include zero, I guess. For me, it is. Maybe for him, because he said he had two conditions. He said that they're pairwise distinct, and their difference is not in the zero divisors of the in ZR, which is his zero divisors. It's this age-old discussion: is zero a zero divisor? I don't know. It divides zero. Is it a zero divisor though? Depends on how you. But the point is, if you have a set of roots which don't differ by a zero divisor, then the eigenspaces are independent subspaces, in the sense that their sum is in fact equal to their direct sum, which is tantamount to saying that if you take a subset of vectors with them taken from the different components, then any selection like that will be linearly independent. It goes back to that independent subspace discussion we had in linear, which I guess extends here to modules. Yeah. Anyway, thanks guys. I'm sorry I went over, but I started late, so